Thanks for spending this time with us. Before we begin, if you'd like, you can share in the comments the first moment you remember really noticing the stars. Whether it was a clear night, far from city lights, a place you traveled to once, or a quiet moment that stayed with you. There's no need to explain it fully. Just the memory itself is enough. Tonight, we're exploring something that unfolds far more slowly than anything we experience in everyday life. The life of a star. Stars live on timescales that stretch far beyond human memory. They are born gradually, change almost imperceptibly, and move toward stillness with a patience that makes ordinary time feel hurried by comparison. When we look up at the night sky, stars appear fixed and unchanging, as though they exist outside of time itself. Night after night, year after year, the same points of light return to the same places. But this stillness is an illusion created by scale. Stars are not static objects. They are processes. They evolve. They age. And over immense spans of time, they move through distinct stages of existence. The reason their lives feel quiet is not because nothing is happening, but because everything is happening slowly. So slowly that human perception cannot follow the changes as they occur. Tonight, we're going to slow those lives down even further, not to dramatize them, and not to compress them into moments of spectacle, but to let them unfold at their natural pace. This is an exploration of how stars come into being, how they settle into long periods of balance, and how, over immense stretches of time, they move toward stillness. If you've ever found yourself wondering how something so bright can also be so patient, you're not alone. There's no need to hold on to that question. Just let it rest quietly in the background as we begin. To understand the life of a star, we first need to adjust how we think about time itself. Human life is shaped by change that happens quickly enough to notice. Days pass, seasons shift, years accumulate. Even the slowest changes we experience, erosion, aging, climate, still unfold on timescales that fit within memory. Stars operate on a different clock. A star can spend tens of millions of years forming before it ever begins to shine. Once it does ignite, it may remain in a stable state for billions of years, longer than complex life has existed on Earth. From our perspective, that stability looks like permanence. But in physics, stability does not mean inactivity. It means balance. A star exists in a constant negotiation between opposing forces. Gravity pulls inward, drawing matter toward the star's center, trying to compress it into a denser and denser state. At the same time, energy generated deep within the star pushes outward, resisting collapse. As long as these forces remain in equilibrium, the star appears calm, quiet, still. This long middle phase, sometimes lasting the vast majority of a star's life, is where most stars spend their time, not exploding, not collapsing, simply existing. And that existence, though outwardly uneventful, is where the true character of a star is formed. Long before a star reaches this balanced state, it begins in a form that barely resembles a star at all. Stars do not begin as points of light. They begin as regions of cold, diffuse matter spread thinly across space. Vast clouds of gas and dust drift through galaxies, so sparse that they would feel nearly empty by human standards. These clouds can stretch for hundreds of light years, their material scattered so gently that nothing about them suggests urgency or direction. Within these clouds, small variations appear. A region may become slightly denser than its surroundings. The difference can be subtle, almost imperceptible, but gravity responds even to the smallest imbalance. Over time, that denser region begins to pull more material toward itself. This process is slow, so slow that millions of years can pass before anything recognizable begins to take shape. There is no sudden moment of birth, no clear dividing line between before and after, only gradual gathering. As material accumulates, the region grows warmer, not from any external source, but from compression. Gravity converts motion into energy. Temperature rises gently, pressure increases, and still nothing shines. At this stage, the forming star is known as a protostar. It is not yet a star in the full sense, but it is no longer just a cloud. It is a structure in progress, shaped by forces that will define it for billions of years to come. Eventually, conditions at the core of the protostar continue to change. Density increases, temperatures climb, atoms move faster, colliding with greater energy, and at a certain threshold, something new becomes possible. Nuclear fusion. This is not fire. There is no flame. Fusion is a rearrangement of matter itself. Hydrogen nuclei begin to combine, forming helium and releasing energy in the process. When this reaction becomes sustained, the star does not erupt into sudden brilliance. It stabilizes. Fusion provides an outward pressure that balances gravity's inward pull. This balance marks the true beginning of a star's long, steady life. The star arrives not through drama, but through equilibrium. From this point forward, it enters the phase that will define most of its existence, a period of remarkable stability during which the star will shine quietly for millions or billions of years, changing so slowly that from one human lifetime to the next, it appears almost unchanged. This is the slow life of stars, a life defined not by sudden events, but by long stretches of balance, a life where stillness is not the absence of activity, but the presence of enduring structure. Once a star settles into stability, its life becomes defined by balance, not a fragile balance and not a temporary one, but a deep, enduring equilibrium that can last for billions of years. From the outside, this phase appears uneventful. The star shines with a steady brightness, night after night, century after century. Its position in the sky barely changes. Generations rise and fall beneath it while the star remains, quietly doing what it has always done. But beneath that calm surface, an extraordinary process is unfolding, continuously, patiently, without pause. At the heart of every stable star is a simple tension. Gravity presses inward, pulling matter toward the center with relentless consistency. Left alone, gravity would cause the star to collapse in on itself, growing denser and hotter as it shrinks. Opposing this inward pull is energy. Deep within the star's core, nuclear fusion converts matter into energy. Hydrogen nuclei combine, forming helium, and in the process, a small amount of mass is transformed into energy. That energy moves outward, creating pressure that resists gravity's compression. As long as these two forces remain in balance, the star endures. This state is known as hydrostatic equilibrium, though the term itself can sound more rigid than the reality it describes. The balance is not static. It is dynamic, constantly adjusting. Fusion rates fluctuate slightly. Pressure shifts. Gravity responds. The star continuously fine-tunes itself, maintaining stability through constant change. This is the phase where a star spends most of its life. For a star like our Sun, this period lasts around 10 billion years. Larger stars burn through their fuel more quickly, shining brighter, but living shorter lives. Smaller stars burn slowly and patiently, potentially shining for trillions of years, far longer than the universe has existed so far. This difference in lifespan is one of the quiet truths of stellar life. Brilliance often comes at the cost of longevity. Modesty, in cosmic terms, can mean endurance. As a star remains in this balanced state, it does not remain entirely unchanged. Its core slowly evolves. Hydrogen fuel is gradually consumed. Helium accumulates. The composition of the core shifts almost imperceptibly over time. From one moment to the next, nothing seems different. From 1 million years to the next, still very little appears to change. But across hundreds of millions and billions of years, the transformation becomes inevitable. The star's life is not defined by sudden events. It is defined by accumulation. Each fusion reaction removes a tiny amount of hydrogen from the core. Each reaction adds a bit more helium. Slowly, quietly, the conditions at the center drift. This gradual drift is what gives stellar life its slow, measured character. Nothing is rushed. Nothing is abrupt. The star is not moving toward an ending so much as it is moving through time. And time, for a star, is vast. During this long Middle Age, the star establishes relationships with its surroundings. Its light warms nearby space. Its gravity shapes the orbits of planets, dust, and gas. In some cases, it becomes the anchor for entire systems. Worlds forming, evolving, and changing under its steady influence. The star does not need to be dramatic to be important. Its constancy is what allows complexity to arise around it. Life, where it exists, depends not on sudden change, but on reliable conditions. Stable light, predictable energy, a consistent rhythm of day and night. In this sense, the quiet middle of a star's life is its most generous phase. Yet even generosity has limits. As hydrogen in the core becomes less abundant, the balance begins to shift. Fusion continues, but the conditions slowly change. Pressure adjusts, gravity responds. The star remains stable, but not permanently so. These changes do not announce themselves. There is no signal that marks the beginning of transition. The star simply continues, carrying within it the record of everything it has already burned. From the outside, nothing looks different. The star still shines, still holds its place, still appears timeless, but internally, the slow march of stellar time continues. This is the quiet truth of stars. Stillness is not the absence of change. It is change unfolding at a pace that invites patience. As we continue, we'll move deeper into this long balance, looking at how different stars experience it differently, how mass shapes destiny, and how the slow use of fuel quietly prepares every star for the next phase of its life. Nothing sudden, nothing rushed, just time doing what it does best. If time is the language of a star's life, then mass is its grammar. From the moment a star begins to form, its mass quietly determines almost everything that follows. How bright it will shine, how long it will remain stable, and how it will eventually move toward stillness. Two stars can be born from similar clouds, ignite in similar ways, and shine with similar light, yet live profoundly different lives, simply because one gathered more matter than the other. This difference does not announce itself early. In the beginning, stars look remarkably alike. They settle into balance. They shine steadily. They appear calm. But beneath that calm, mass is already shaping the future. A more massive star experiences stronger gravity. That gravity compresses the core more tightly, raising temperatures and pressures to higher levels. Fusion proceeds more rapidly. Energy flows outward with greater intensity. The star shines brighter, but brightness comes at a cost. Fuel is consumed more quickly. The balance between gravity and energy must be maintained at higher output. The star lives faster. Less massive stars, by contrast, live quietly. Their gravity is gentler. Their cores are cooler. Fusion proceeds slowly and efficiently. They do not rush. Some of the smallest stars, red dwarfs, burn their fuel so patiently that they may outlive every other structure in the universe. Trillions of years could pass, while they continue shining steadily long after larger stars have completed their life cycles. In this way, mass does not create drama. It creates tempo. Large stars live intensely. Small stars live persistently. Neither is better. Neither is incomplete. They simply follow different paths through the same physical rules. As stars remain in their long phase of balance, their mass quietly governs how their internal structures evolve. In larger stars, multiple layers of fusion may develop over time. Different elements form at different depths. Complex internal motion redistributes energy and matter. In smaller stars, the structure remains simpler. Fusion proceeds slowly, and the interior remains more uniform. But in all cases, the star is not static. Even during its calmest phase, it is slowly preparing for what comes next. Hydrogen is steadily converted into helium. The core's composition changes. The balance adjusts in response. This is not preparation in a purposeful sense. The star is not moving toward an outcome. It is simply following physics, and physics does not hurry. What makes this process feel especially quiet is how little changes on observable timescales. A star can remain in this phase for longer than civilizations rise and fall, longer than continents drift, longer than species emerge and disappear. From the star's perspective, nothing remarkable is happening. From ours, everything is. because this long stability is what allows galaxies to remain structured and planetary systems to persist. It is what allows time to stretch long enough for complexity to take root. Eventually, however, the slow accumulation of change reaches a threshold, not suddenly, not catastrophically, just enough to alter the balance. When hydrogen in the core becomes scarce, fusion begins to slow, outward pressure weakens. Gravity responds by gently compressing the core further. The star does not fail. It adjusts, and in that adjustment, a new chapter of stellar life begins to take shape. We'll move into that transition next, not as an ending, but as a continuation of the same slow logic that has guided the star from the beginning. For most of its life, a star exists in a state so stable that it can feel almost permanent. But permanence, in stellar terms, is simply change stretched across immense time. Nothing holds perfectly forever. As hydrogen in the core continues to diminish, the balance that has defined the star for so long begins to change, not abruptly and not violently, but quietly. Fusion slows at the center. With less energy being produced, there the outward pressure that once matched gravity weakens slightly. Gravity responds, as it always does, by pulling inward. The core begins to contract. This contraction does not signal failure. It is a continuation of the same physical conversation that has guided the star from the beginning. Gravity presses, matter responds, energy adjusts. As the core compresses, it heats up. Temperatures rise, not because new fuel has appeared, but because gravity is doing what it has always done, converting motion and compression into heat. Around the core, something subtle happens. Hydrogen fusion, which once occurred at the very center, shifts outward into a surrounding shell. Fusion continues, but no longer in the same configuration. The star is still producing energy. It is still shining, but its internal structure is changing. From the outside, this change is not immediately obvious. The star may grow slightly brighter. It may expand slowly. Its surface temperature may shift. These changes unfold over millions of years, slow enough that they feel almost invisible, yet they mark the beginning of a new phase. The long middle age of the star is giving way to something more dynamic, not dramatic, but transitional. As the star expands, its outer layers drift farther from the core. Surface gravity weakens. The star's light spreads across a larger area. This is how many stars enter what we call a giant phase. The word giant can sound misleading. It suggests sudden growth or spectacle. In reality, this expansion is gentle. The star swells, gradually responding to internal changes that have been building quietly for eons. In this phase, the star is not unstable. It is adjusting. It is finding a new balance. under slightly different conditions. And this idea, that change does not require disruption, is central to understanding the slow life of stars. Stars do not rush toward endings. They move through transitions, guided by the same rules that governed their beginnings. For stars with modest mass, this expansion can lead to long periods of gentle luminosity. They may spend hundreds of millions of years in this expanded state, shining with a softer, broader light. For more massive stars, the process unfolds more quickly. Their stronger gravity drives faster internal changes. Fusion proceeds through heavier elements. Each stage builds upon the last, stacking layers of nuclear activity within the star. But even here, the pace is not frantic. Compared to human experience, it remains slow, measured, predictable. What feels significant to us? A star, changing size, shifting color, altering brightness, dash, dash, is simply the natural result of physics continuing to operate. There is no moment when the star realizes it has changed, no signal that marks a turning point. There is only the steady unfolding of cause and effect. This gradual shift is one of the most calming aspects of stellar evolution. Even when a star leaves its longest stable phase, it does not fall into chaos. It enters a new pattern. And that pattern, too, can last longer than human history. As we move forward, we'll follow stars as they continue through these later stages. Not toward destruction, but toward resolution, toward forms of stillness that look different from the ones they began with, yet remain governed by the same quiet rules. Nothing sudden, nothing rushed, just the universe allowing matter to explore what balance looks like under changing conditions. As the balance within a star continues to adjust, its future narrows, not in urgency, but in possibility. By this stage, mass has already written most of the story. What remains is not uncertainty, but follow-through. For stars with lower and moderate mass, the path forward becomes increasingly calm. After long periods of expansion and internal rearrangement, fusion in the core eventually reaches its natural limit. Not because something goes wrong, but because the available fuel for that phase has simply been used. When fusion can no longer proceed in the same way, the star does not collapse dramatically. Instead, it begins to let go. Its outer layers drift outward, moving slowly away from the core. This shedding is gentle, unforced. Material that once belonged to the star returns to the surrounding space, joining the diffuse clouds from which other stars may one day form. What remains at the center is a compact, stable core, no longer producing energy through fusion, but still held together by gravity and pressure. This remnant is quiet, dense, hot at first, then gradually cooling over immense spans of time. It does not shine because it is generating new energy. It shines only with stored heat, slowly releasing what it already contains. Over billions of years, even that faint glow fades. What remains is stillness, not absence, but equilibrium reached. For more massive stars, the outcome is shaped by stronger gravity and faster internal evolution. Their cores pass through multiple stages of fusion, forming heavier and heavier elements. Each stage lasts less time than the one before it, not because the star is rushing, but because gravity demands higher temperatures and pressures to sustain each new balance. Eventually, fusion can proceed no further. At that point, gravity becomes dominant. But even here, the universe does not default to chaos. The star's core settles into one of several stable configurations, depending on its remaining mass. In every case, the result is a form that can endure, not an ending, but a state. These final forms, compact, dense, and quiet, persist far longer than the bright phases that preceded them. They do not evolve quickly. They do not demand attention. They simply remain. This is an important detail, often overlooked. The most dramatic moments in a star's life are also the shortest. The longest chapters are the calm ones. Stillness is not what follows activity. It is what dominates the timeline. Across the universe, countless stellar remnants exist, silent records of lives that unfolded slowly, guided by the same physical principles from beginning to end. They do not mark failure. They mark completion in the most neutral sense, a process carried through, energy redistributed, matter reorganized, balance found again, this time without light. And even in this quiet state, the star is not separate from the larger story. Its material contributes to future structures. Its gravity continues to influence its surroundings. Its existence remains woven into the fabric of space. Nothing is wasted. Nothing is erased. The universe does not discard outcomes. It incorporates them. As we come closer to the end of this exploration, one final perspective remains. Not about how stars end, but about what their slow lives reveal. About time itself, about patience as a natural property of the universe, and stillness not as an absence, but as a lasting condition. That is where we'll rest next. By the time a star reaches its quietest state, nothing has gone wrong. There is no failure in this stillness, no sense that something has ended too soon. What we are seeing is not decline, but completion. In the universe, processes do not conclude with punctuation. They conclude with balance. The final forms that stars take are not temporary pauses. They are stable arrangements of matter and energy, shaped by the same physical rules that governed every earlier phase. Gravity still holds, pressure still resists collapse, structure remains intact. The difference is not in stability, but in activity. The star no longer needs to change. For stars that end as compact remnants, time stretches even further. Their evolution slows to a near standstill. Cooling occurs over billions, then trillions of years. Each moment passes with almost no visible difference from the last. From a human perspective, this can feel like an ending, but on cosmic scales, it is simply another state, dash, 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 one that lasts far longer than the luminous phases that came before it. This is a pattern that appears again and again in astrophysics. Rapid processes give way to slow ones. High energy gives way to equilibrium. Motion gives way to rest, not because motion is exhausted, but because balance has been reached. Stillness, in this sense, is not empty. It is full of structure. The matter within a stellar remnant remains precisely arranged. Quantum forces govern its interior. Gravity maintains its shape. Time continues to pass. Nothing has disappeared. What has changed is the rate at which things happen. This extreme slowing is one of the most consistent features of the universe. As systems evolve, they tend to move toward states that require less change to maintain. Energy spreads out. Gradients soften. Differences even out. This does not mean the universe is fading away. It means it is settling. Stars are simply one expression of this broader tendency. Their lives begin with gathering, move through long balance, and end in enduring stillness. Not because they are fragile, but because the universe favors stability. And this stability is not rare. It is the dominant condition. Across galaxies, most matter exists in quiet forms. Most time passes without events. Most structure persists rather than transforms. The dramatic moments, bursts of light, rapid change, visible transformation, dash, dash, are brief by comparison. They stand out only because they are exceptions. Stillness is the rule, and when we view stellar life through this lens, its slow pace begins to feel less unusual and more representative. Stars are not special because they shine. They are special because they endure. Their brightness is temporary. Their structure is lasting. This realization gently reframes how we think about beginnings and endings. A star does not end when it stops shining. It simply stops changing in ways we can easily see. Its existence continues embedded in the same space-time, governed by the same laws. And as long as those laws remain consistent, there is no reason for that existence to disappear. As we move into the final chapter, we'll step back from individual stars and look at what their slow lives suggest more broadly about time, patience, and why the universe so often chooses to last rather than conclude. If stars seem calm to us, it is because we are watching them from the wrong scale. The universe does not move slowly or quickly on its own. Speed only exists in comparison, and when human time is placed next to stellar time, the difference reshapes how everything feels. A star's life is not measured in events, but in endurance. From the moment a star settles into balance, It begins a long relationship with time dash dash. One defined not by change, but by consistency. For millions of years at a time, nothing about the star appears different. Its light remains steady. Its size remains stable. Its position in the sky hardly shifts. This does not mean the star is frozen. It means the processes within it operate on scales far larger than perception. At the center of the star, fusion continues relentlessly. Hydrogen nuclei combine, helium accumulates, and energy flows outward in a constant stream. Each individual fusion reaction is brief, but the collective process unfolds over billions of years. The star is not waiting for something to happen. It is already happening, just slowly enough that it feels like stillness. This is one of the quiet truths of astrophysics. Most change in the universe happens beneath thresholds of notice. We tend to focus on moments, birth, explosion, collapse, because they compress change into something visible. But stars spend nearly all their lives outside of those moments. They exist in states where cause and effect are stretched so thin that transformation becomes subtle. Time, in these states, feels different. For a star like our Sun, 10 million years pass without altering its character in any meaningful way. From a human perspective, 10 million years is unfathomable. From the star's perspective, it is routine. This mismatch is why stars appear eternal. They are not exempt from time. They are simply aligned with it differently, and this alignment affects everything around them. Planets form and settle into orbits because stars remain stable long enough to allow it. Atmospheres persist because stellar output does not fluctuate wildly. Life, where it emerges, depends on this patience, not on brilliance, but on reliability. Stars teach us that duration matters more than intensity. The brightest stars burn fastest. The quiet ones last. Some of the smallest stars in the universe shine so slowly that they will outlive almost every other structure we know. They will continue glowing long after galaxies have drifted apart, long after larger stars have faded. In that sense, time itself bends toward stillness. As systems evolve, they tend to move toward states that change less, not more. Stars are a perfect expression of this tendency. They begin in motion, gathering, collapsing, heating. They pass into balance, steady, luminous, enduring, and eventually they move toward states where almost nothing changes at all. This is not decay, it is settling, and it happens not because time runs out, but because balance becomes easier to maintain. The universe does not rush its structures. It allows them to persist. As long as the rules permit, stars simply follow that allowance. They do not hurry toward endings. They drift toward stability, and that drift, slow, quiet, unforced, is what gives stellar life its character. As we continue, we'll look more closely at how this patience shapes different stars in different ways, how mass alters the pace of time itself, and why no two stellar lives unfold at exactly the same speed. Time shapes every star, but mass decides how that time is spent. From the moment a star forms, its mass quietly governs the rhythm of its life, not as a dramatic force, but as a steady influence that sets the pace for everything that follows. Two stars can be born from similar clouds of gas and dust, ignite in similar ways, and shine with comparable light, yet live profoundly different lives, simply because one gathered more matter than the other. This difference does not announce itself immediately. In their earliest stable years, stars often look remarkably alike. They settle into balance, they shine steadily, they appear calm and enduring, but beneath that calm surface, mass is already shaping the future. A more massive star feels gravity more intensely. That stronger gravity compresses the star's core more tightly, raising temperature and pressure to higher levels. Fusion reactions proceed faster. Energy flows outward with greater force. The star shines brighter, but brightness comes with consequence. Fuel is consumed more quickly. The balance between gravity and outward pressure must be maintained at a higher output. The star lives at a faster pace. Less massive stars experience a different relationship with time. Their gravity is gentler. Their cores are cooler. Fusion proceeds slowly and efficiently. Energy is released at a measured rate, allowing the star to persist far longer. Some of the smallest stars in the universe, red dwarfs, shine so patiently that their lifespans extend into trillions of years. They burn their fuel so conservatively that none have yet reached the later stages of stellar life. In this way, mass does not create drama. It creates tempo. Large stars live intensely. Small stars live persistently. Neither path is more complete than the other. They are simply different expressions of the same physical rules. As stars remain in their long period of balance, mass continues to influence their internal structure. In larger stars, fusion can occur in layered regions, with different elements forming at different depths. Energy moves outward through complex flows, reshaping the star from the inside. In smaller stars, the structure remains simpler. Fusion occurs more uniformly, and internal mixing keeps the star relatively consistent throughout. But in all cases, the star is not static. Even during its calmest phase, it is slowly changing. Hydrogen is steadily converted into helium. The core's composition shifts, almost imperceptibly, from moment to moment, but inevitably over time. What makes this change feel so quiet is how little of it is visible. A star can remain stable for longer than continents drift, longer than species evolve, longer than civilizations rise and fall. From the star's perspective, this is simply how existence works. From ours, it feels like permanence, but permanence is only an illusion created by scale. Eventually, the slow accumulation of change reaches a threshold, not suddenly, not catastrophically, just enough to alter the balance that is held for so long. When hydrogen in the core becomes scarce, fusion slows, outward pressure weakens. Gravity responds by gently compressing the core further. The star does not fail. It adjusts, and in that adjustment, a new phase of stellar life begins to take shape. This transition is not an ending. It is not a breakdown. It is the same physics continuing, under slightly different conditions. Mass determines how dramatic that transition will be, how quickly it unfolds, and how much the star's outward appearance will change. For some stars, the change is gentle and prolonged. For others, it is faster and more pronounced. But in every case, the process remains governed by patience. Stars do not rush through their lives. They follow the pace set by their mass, responding to gravity and energy with quiet consistency. As we move forward, we'll follow stars as they continue beyond their longest period of balance, not toward chaos, but toward new forms of stillness, forms that look different from the calm shine we recognize, yet remain just as stable. When a star finally begins to move beyond its longest period of balance, the change is so gradual that it almost feels like nothing is happening at all. From the outside, the star still shines. Its light still reaches across space. Its presence still feels steady, but internally, the conditions that supported that long equilibrium are slowly giving way to something new. This transition does not arrive as a moment. There is no single instant when a star leaves one phase and enters another. Instead, the star drifts. Fusion in the core becomes less efficient as hydrogen is depleted. The outward pressure that once matched gravity weakens just enough to allow gravity to respond. The core contracts slightly. As it does, it heats up, not because new fuel has appeared, but because compression itself generates energy. This rising temperature allows fusion to continue, but now in a different configuration. Hydrogen burning shifts outward into a surrounding shell, encircling the core rather than occupying it. The star remains stable, but the balance has changed. These internal adjustments unfold over millions of years. From one century to the next, there is no visible difference. From 1 million years to the next, the change is still subtle, and yet, over time, the star's outer layers begin to respond. They expand, not suddenly and not violently. The star grows larger, its surface moving farther from the core, its gravity at the surface weakening. As the star expands, its light spreads across a wider area. Its surface temperature may decrease even as its total brightness increases. This is how many stars enter what we describe as a giant phase. The word giant can suggest drama, but the reality is quiet. The star does not swell overnight. It takes its time. Hundreds of millions of years may pass as the star slowly reshapes itself, responding to internal conditions that have been evolving since its formation. In this expanded state, the star is not unstable. It has simply found a new equilibrium. Gravity still pulls inward. Energy still flows outward. The star continues to exist within the same physical rules. What has changed is the scale at which those rules now operate. This phase reveals something important about how the universe handles transformation. Change does not require disruption. A system can evolve without breaking. Stars do not leap from one identity to another. They slide. Each state emerges naturally from the one before it, guided by the same forces, obeying the same constraints. For stars with moderate mass, this expanded phase can last a very long time. They may spend hundreds of millions of years in this broader, cooler state, shedding small amounts of material into surrounding space. Through gentle outflows, nothing is wasted. The matter released by the star joins the interstellar medium, enriching it with elements forged during the star's life. This material may one day become part of new stars, new planets, new structures. The star's slow change becomes part of a larger cycle. For more massive stars, the process continues through additional layers of fusion. Heavier elements form at the core. Each new stage requires higher temperatures and pressures to maintain balance. As before, mass determines pace. Larger stars move through these phases more quickly, not because they are unstable, but because gravity demands more from them. Even so, the transitions remain orderly. There is no hurry. Physics proceeds step by step, allowing each configuration to exist for as long as it can. This extended period of gentle change is often overlooked because it lacks spectacle, but it is one of the most revealing aspects of stellar life. It shows us that the universe favors continuity over disruption, adjustment over collapse. Stars do not resist change, and they do not chase it. They respond, and they respond at a pace set not by urgency, but by balance. As we continue, we'll move closer to the later stages of stellar life, not as endings, but as long-lasting outcomes, forms that persist quietly long after light has faded and change has slowed to nearly nothing. As stars move through these later phases of change, what becomes increasingly clear is that the universe does not rush them toward disappearance. Instead, it guides them toward states that can last. After fusion can no longer continue in the same way, a star does not unravel. It does not fall apart. It settles. For stars with lower and moderate mass, this settling is especially gentle. Over long periods of time, their outer layers continue to drift away, not in sudden bursts, but in slow, steady outflows. What remains at the center grows smaller and denser, its internal activity diminishing. Fusion no longer drives the star. There is no longer a need to balance gravity with newly generated energy. And yet, the object that remains is not unstable. It is supported by different forms of pressure, forces that arise not from heat, but from the fundamental behavior of matter itself. The star has transitioned from a luminous engine into a compact structure, dense, quiet, persistent. At first, this remnant still carries warmth from its earlier life. It glows faintly, releasing stored heat into surrounding space. Over billions of years, that warmth slowly dissipates. Cooling happens at a pace that once again defies intuition. Entire epochs pass, while the object changes only slightly. From one human lifetime to the next, it appears unchanged. This is not dormancy, it is stability. The universe is filled with such stable forms, structures that no longer transform rapidly, yet remain deeply integrated into the cosmic landscape. They exert gravity. They influence their surroundings. They participate in the long-term architecture of galaxies. Nothing about them is temporary. For more massive stars, the route to stillness follows a different path, but the outcome shares the same character. As their internal fusion processes reach natural limits, gravity again becomes dominant. The core contracts further, finding new balances at extraordinary densities. Matter arranges itself into configurations that can withstand immense gravitational pressure. These states are not fleeting. They are among the most enduring objects in the universe. Once formed, they persist for timescales that dwarf their earlier luminous phases. What is striking about all of these outcomes is how little they resemble endings. There is no sense of failure, no collapse into chaos. Instead, there is resolution, a system that has explored its available paths, settles into a configuration that can last. This pattern extends far beyond stars. Across physics, systems tend to move toward arrangements that require the least ongoing change to maintain. Energy spreads out, gradients soften, motion gives way to equilibrium. Stars simply make this tendency visible. Their bright lives draw attention, but their quiet states dominate time. Most of the universe exists in these long-lasting forms, stable, persistent, and unhurried. The dramatic moments that capture imagination are brief interruptions in a much longer story. And when we widen our view to cosmic timescales, those interruptions fade in significance. What remains is structure, structure that holds, structure that lasts. This is why stillness in astronomy is not emptiness. It is presence without urgency. A star that no longer shines has not vanished. It has simply entered a phase. where change has slowed to nearly nothing, and nearly nothing, when stretched across billions of years, becomes its own kind of continuity. As we move forward, we'll step back from individual stellar lives and look at what this pattern suggests more broadly about time, patience, and why the universe so often favors endurance over resolution. When we step back far enough, stellar life begins to resemble something broader than astronomy. It begins to resemble a pattern. Stars do not race toward completion. They do not seek dramatic resolution. They move gradually, consistently, toward states that demand less change over time. This is not unique to stars. It is how the universe behaves. Across every scale we can observe, systems tend to move toward arrangements that are easier to maintain than to alter. Energy disperses, gradients soften, motion becomes more evenly distributed. In physics, this tendency is not framed as loss. It is framed as balance. Stars simply make this tendency visible over long stretches of time. Their lives begin in gathering. Matter drawn together by gravity, motion converted into heat, structure emerging from diffuse beginnings. They pass into long periods of balance, light flowing steadily outward, gravity pressing inward, time stretching wide enough for planets, systems, and sometimes life to exist, and eventually they move into states where almost nothing changes, not because something has ended, but because nothing needs to. These later states are not pauses. They are conclusions in the physical sense, not conclusions that close a story, but conclusions that resolve tension. Gravity is balanced, pressure holds, energy no longer needs to be generated. The system has learned how to remain. This is one of the quiet lessons hidden inside stellar evolution. Time does not always move toward complexity. Sometimes it moves toward simplicity. Not simplicity as absence, but simplicity as sufficiency. A configuration that does not require further rearrangement is not incomplete. It is complete enough. This is why stillness appears again and again as a final form in the universe, not as emptiness, but as stability. Most matter in the universe exists in these long-lasting states. Most time passes without events. Most structure persists rather than transforms. The dramatic moments, birth, ignition, expansion, are brief chapters. They stand out because they are rare, not because they are central. Stars teach us this by contrast. Their brightest moments are the shortest. Their quiet ones are the longest. And when we measure existence in time rather than intensity, it becomes clear which phase truly defines them. The same star that shines brilliantly for billions of years may exist in a quiet state for trillions more. From the universe's perspective, that quiet state is the main event. This perspective changes how we think about endings. An ending suggests disappearance, a stopping point, a boundary beyond which nothing continues. But stellar life does not support this idea. What it supports, instead, is continuity with diminishing urgency. Change slows, structure remains, time stretches, nothing collapses into nothingness. It simply settles. This settling is not passive, it is active stability. Matter arranged precisely enough to persist under the forces acting upon it. And once such an arrangement is reached, there is no reason for it to unravel. The universe does not undo balance. It preserves it. This is why the cosmos feels calm when viewed across long spans of time. Not because nothing happens, but because what happens tends to last. Stars do not rush toward silence. They drift into it, and in doing so, they reveal something fundamental about the nature of time itself. Time is not always a countdown. Sometimes it is a widening, a slowing, a process that gently reduces the need for change. As we approach the final chapter of this exploration, we won't be looking for conclusions or answers that close the subject. Instead, we'll allow this pattern of slow, unfolding, and quiet persistence to shape how the question rests, not as something solved, but as something understood well enough to no longer press forward. When we think about stars, we instinctively think about light, brightness, color, presence in the night sky. Light is how stars announce themselves. It is how we notice them, how we study them, how they become part of human awareness at all. But light is not the most enduring thing about a star. It is only the most visible. For most of a star's existence, light is not its defining feature. Time is. A star may shine brilliantly for billions of years, but it will exist far longer in forms that no longer glow. This is difficult to grasp because light dominates attention. When light fades, we tend to think something has ended. But in stellar terms, light fading does not mean disappearance. It means the story has shifted to a scale that no longer announces itself. Once a star settles into its quiet state, its influence does not vanish. Its gravity remains. Its mass remains. Its place in the structure of the galaxy remains. What has changed is not existence, but expression. The star no longer broadcasts energy outward. It no longer shapes its surroundings through radiation. Instead, it participates quietly as a stable point of mass, a component in the long-term architecture of space. Galaxies are filled with these silent participants. They do not draw attention. They do not evolve quickly. They simply remain. And because they remain, they shape what comes next. Gravity does not require light to function. Structure does not require brilliance to persist. The universe is not built around visibility. It is built around endurance. This becomes especially clear when we consider how much of the universe exists beyond what we can directly observe. Most matter does not shine. Most structure does not announce itself. Most time passes without events dramatic enough to register on human scales. Stars are a reminder of this imbalance. Their shining years make them noticeable, but their quiet years make them representative. They show us that the universe does not prioritize intensity. It prioritizes stability, and stability, once reached, tends to last. This has an interesting effect on how we think about cosmic history. History, as we usually imagine it, is a sequence of events, beginnings, transitions, endings. But on cosmic timescales, history becomes something else. It becomes a gradual redistribution of matter and energy toward states that require less change to maintain. Stars participate in this not as exceptions, but as examples. They gather, they shine, they settle, and then they remain, quietly, indefinitely. From a distance large enough, the universe looks less like a story and more like a landscape. Not a landscape frozen in time, but one where the slowest features dominate, simply because they last the longest. Mountains outlast storms. Continents outlast waves. Stellar remnants outlast stellar light. This is not decay. It is persistence, selecting what endures. And once we see this pattern clearly, the idea of stillness changes. Stillness is no longer absence of motion. It is motion reduced to its most durable form. A star that no longer shines has not lost relevance. It has entered the phase that defines most of its existence. The universe does not mark this moment as an ending. It does not draw a line. It simply continues operating under the same rules as before. Light was never the point. Balance was. And balance, once found, does not ask to be undone. As we continue, we'll allow this idea to remain present, not as a conclusion, but as a background understanding, a way of seeing stars, not as moments of brilliance, but as participants in a universe that quietly favors what lasts. By the time we reach this point, nothing new needs to be introduced. The shape of stellar life has already revealed itself, not as a sequence of dramatic moments, but as a long movement toward stability. Stars begin in gathering, pass through extended balance, and eventually arrive at forms that require very little change to endure. What remains now is simply to allow that pattern to rest. A star that has reached its quiet state does not stand apart from the universe. It becomes part of its background. Its mass continues to participate in gravity. Its presence continues to shape space locally. Its existence is no longer defined by output, but by persistence. And persistence, on cosmic scales, is the most common condition of all. When we look up at the night sky, we are seeing only a brief window in a much longer story. We see stars during the portion of their lives when light is abundant and easily noticed. But that phase, however long it feels to us, is temporary. Most of a star's existence unfolds outside of visibility. It unfolds in quiet configurations that change so slowly. They feel almost timeless. This does not make those phases less real. If anything, it makes them more representative. The universe is not dominated by moments. It is dominated by durations. What lasts the longest defines the character of everything else. This is why stillness appears again and again as a natural outcome, not because motion has failed, but because motion has resolved, energy has spread, forces have balanced, structure has settled into a form that can persist without effort. There is no requirement for disappearance. Nothing in physics suggests that matter must vanish once it stops changing rapidly. Instead, what we see is a gradual slowing, a gentle reduction in the need for transformation. Stars demonstrate this clearly. Their most active phases are brief, relative to the time they spend simply existing. And when viewed this way, their quiet states are not an epilogue. They are the main body of the story. This perspective subtly changes how we think about time. Time does not always push things forward. Sometimes it allows them to stay. Sometimes the most significant outcome is not what happens next, but what continues. The universe does not move toward silence in the way we often imagine. It moves toward balance, and balance, once reached, does not require resolution. It requires only consistency. Stars do not need to conclude their lives in order to fulfill them. They do not need a final event to justify the time they have taken. Their existence is complete simply by persisting within the rules that shape them, and those rules remain in place. Gravity continues, space continues, time continues. The star's role changes, but the framework does not. This is perhaps the quietest insight stellar life offers. That continuity is not something to be solved. It is something to be noticed. The universe does not rush toward endings. It allows structures to remain as long as they can, and most of the time, they can remain for a very long while. So when the light of a star fades, nothing truly stops. The processes that shaped it have simply reached a state where change is no longer necessary. The universe continues doing what it has always done, holding matter, allowing time to pass, and favoring what lasts. There is no final moment here, no closing boundary, only continuation, quiet and unforced, and within that continuation, the slow life of stars finds its natural stillness, not as an ending, but as a lasting state. By the time a star reaches its quietest state, nothing has gone wrong. There is no sense of failure in this stillness, no indication that something has ended too soon. What has happened is simpler than that. The forces that once demanded constant adjustment have reached a balance that no longer needs to change. The star has not disappeared. It has not withdrawn from the universe. It has simply become part of the background, against which other changes unfold. This is something we rarely notice, because attention is drawn to what moves, what shines, what announces itself. But the universe is not organized around attention. It is organized around endurance. A star that no longer produces light still carries mass, still shapes space around it, still participates in gravity. It remains woven into the structure of its galaxy, quietly influencing motion, without signaling its presence. This is not an exception. It is the rule. Most of the universe exists in states like this: stable, persistent, and unhurried. Most matter is not active in ways we can easily observe. Most time passes without events dramatic enough to be noticed. Stars teach us this, not through what they do, but through how long they remain. Their luminous phases are impressive, but brief compared to the spans of time. They spend simply existing, and this changes how we understand importance. Importance, on cosmic scales, is not about intensity. It is about duration. What lasts the longest shapes everything else around it. Galaxies maintain their structure because most of their mass exists in stable forms. Orbits remain predictable because gravity does not flicker or fade. Even the quiet remnants of stars continue to hold space together long after their light has vanished. This persistence is not dramatic. It does not seek attention. It simply remains, and in remaining, it allows other processes to take place. New stars form from old material. New systems emerge within long-standing frameworks. Nothing needs to be cleared away. For this to happen, the universe does not reset. It builds continuously upon what already exists. This is why stillness is not emptiness. Stillness is structure that no longer needs to rearrange itself. A star that has settled into its final state has reached a configuration that can persist indefinitely under the conditions of the universe. No further transformation is required, and because no transformation is required, time stretches. Billions of years pass with almost no visible change. From one moment to the next, nothing seems different. From one epoch to the next, the difference is still subtle. This extreme slowing is not stagnation, it is resolution. The universe does not demand constant motion. It does not require escalation. It allows systems to stop changing once balance has been found. Stars are simply one example of this broader pattern. Across physics, systems tend to move toward arrangements that require the least ongoing adjustment to maintain. Energy spreads out, differences soften, change becomes less frequent, not because the universe is running down, but because balance is easier to sustain than imbalance. This tendency gives the universe its calm character. When viewed across long spans of time, from close up, there is motion everywhere. From far enough away, there is remarkable steadiness. Stars embody this contrast perfectly. They begin in motion, gathering matter, heating, igniting. They pass through long periods of balance, steady light, predictable output, enduring presence, and eventually they arrive at states where almost nothing changes at all. These final states are not brief. They are the longest chapters in a star's existence. The bright years are what we notice. The quiet years are what define them. And when we recognize this, the idea of an ending loses its urgency. A star does not end when it stops shining. It simply stops changing in ways that draw attention. Its role shifts from participant to framework, from event to structure, and the universe is built far more from structures than from events. This perspective allows the story of stellar life to rest without needing closure. There is no final moment that must be marked, no boundary that must be crossed, only a gradual easing into states that last longer than anything that came before. The universe does not hurry stars toward disappearance. It allows them to remain for as long as they can, and in most cases, they can remain for a very long time. So when the light of a star fades, nothing truly concludes. Time continues, space continues, structure continues. The slow life of stars does not resolve into silence. It settles into presence, quiet, unforced, and enduring.